Okay, let's start. So today we are going to learn combinatorial testing and when to stop testing. So this is today's outline. So basically we have two main topics. First, let's come to combinatorial testing. You may notice from the name of this technique that it is about combinations. So what kind of combinations can we have when we build test cases? For this example from assignment 1, for this function here, we can have test cases like this. So as you can see, it could be viewed as some perhaps equivalent classes for A, B, and C individually, or we can see it as a combination of the values of A, B, and C here. And similarly, if most of the programs nowadays, they have a graphical user interface. For example, if we want to test a registration form, so the inputs could be text, could be some options, and for this form, we could test the combination of all these different input parameters. So the first thing we can combine for combinations are the input parameters. And sometimes we could combine more things together to do the testing. So for example, in some systems, we can do some configurations for the softwares. So what we can do is we can also try to combine different configuration options. So the thing is, we can combine them together, we can build up combinations, but how can we systematically generate the combinations for testing? So this comes to the concept of combinatorial testing. So what we want is to check all the combinations of different system inputs. So the rationale here is that there are some bugs related to the interactions between different pairs of inputs. So that's why we do combinatorial testing. And of course, as we have seen just now, we can combine different input parameters. We can combine different configuration options. And here is another example of combining different configuration options. So this is actually from a report of NIST. And you can see these are different options we can combine together. And you may wonder, what is XP operating system? Do you know what is XP? Yeah, it's a version of Windows. It's a very old version of Windows, actually. And why this is this is a link. You can click on this figure to get to the raw report. And why it uses XP as example here is because this report was written in the early 2020s, and it takes 5 years for NIST to do this report for combinatorial testing. They were spending a lot of effort into this. And if you wonder what is NIST, it's actually the National Institute of Standards and Technology of the US government. So they focus on doing this study of combinatorial testing is because it is actually a very practical way of designing test cases. And you may notice we can also say we can also in their report they also mention combinatorial testing as T-way testing, and we will learn about why it could also be called as T-way testing later. So according to this definition here, so which levels of testing do you think combinatorial testing belongs to? Let's do a quick live poll here. Actually, you should be careful because you see the options are, if you see a radio button here, then there's only one correct answer. And if you see checkbox, there might be multiple correct answers. So actually all of them are correct. So combinatorial testing could be applied to units or integrations or systems. So although in the definition it is called system inputs, I intentionally put the system in, I intentionally use a different font for this system here because this system refers to, could be referring to a function, could be referring to a particular unit of the code. So it doesn't have to be the entire system of the software. So in our first example, you could see that we can even do combinatorial testing for a function, like for the find max, and we can also do combinatorial testing for some more complex software, like whatever browser we can test, right? So it could be applied to all different levels of testing. And another question is, what do you think is the color of box for combinatorial testing? Black, gray, or white? Gray? It's actually a white box. Oh, sorry, it's actually a black box. It's actually a black box because we don't need to think about what's happening inside the software. We just need to care about the combination of different inputs. So it's actually a black box testing technique. And now let's come to the concept of T-way combinations. Just now in the report of NIST, we mentioned that we mentioned the term of T-way testing because combinatorial testing could be referred to, could be described as T-way testing. And T-way testing means we are trying to combine different, we are trying to build different combinations of input parameters to a specific interaction level. And this interaction level is often denoted as T. So for example, if we do a two-way testing, which is a pairwise testing, it means that we want to cover all pairs. We want to cover all the possibilities for all the pairs, individual pairs of input parameters. It matters how many values per parameter could have. So for example, if we have 3 pairs, and each parameter can take 3 different values, then we need 9 test cases in this case. We may need 9 test cases, but we may need less. We will see later. So if we do a 3-way testing, we will need to ensure all the triples are covered, and so on. So this is called T-way testing, and the interaction level determines how many individual input parameters do we want to combine together. So there's a problem of combination testing, a combination explosion. We have actually learned a path explosion before, and do you still remember where did we learn it? Okay, that's good. So actually we learned it in lecture 6. And let's consider that we have n parameters, and we want to do a 2-way combinations. We want to find all the pairs out of the n parameters. So how many pairs can we have here? Yeah, Cn2 actually. And this is how it is calculated. And if we plot this, formula here, this is what we will get. And the x-axis is actually the number of n, and the y-axis is the number of pairs we will have. And you can see that we will have too many pairs, even if we do a pairwise, even if we do a two-way combination. And if we increase the number of n, we will get more test cases. If we increase the number of interaction level, we will also have more test cases. And that is often not that is infeasible in real world cases to have this many test cases, because this is very it is very common that a complex system could have many input parameters. So how do we limit the number of test cases we could have? So the first thing we can do is we can limit the interaction level. So which means that we can limit the number of t here. And how do we determine the number of t? So again, from the report of NIST, they actually mentioned that most of the software bugs could be found by covering all the combinations or all the possibilities of one or two parameters. So which means that we just do one-way combinatorial. One-way combinatorial testing just means that we need to test every possible value for every parameter, or every possible equivalent class for every parameter. And this is a report from their findings. So they have tested different targets. For example, medical devices, browsers, servers, and the NASA distributed database. So we can see that if we apply two-way combination testing, we can cover at least 70% of the faults. So normally we can limit the interaction level to level 2. So which means that we just need to do pairwise combinatorial testing most of the time. So the x-axis here is actually the interaction level t. And just now I mentioned that we can save some test cases. We don't need to exhaustively try out all the combinations when we build up the test suite. So let's see how we can do this and how can we build the test suite for combinatorial testing. So here's the question: do we just exhaustively generate the combination? And the short answer is no. And let's see why. The reason is that we can use a concept called covering arrays. And a covering array is basically a matrix, or it could be represented as a table. And let's see what is inside this covering array. So it is actually an n times k matrix where the rows represent the test cases, and the columns represent the parameters. And then each cell is a specific value for a parameter in this table or in this covering array. And it could often be denoted like this if we add more information. So apart from the number of test cases and the number of parameters we can have, we can also specify the interaction level, and we can also specify the number of possible values that each parameter can take, assuming that they are having the same number of values. And covering arrays are very useful. They can help us to improve the efficiency because we can save some test cases by building covering array. And it has a very high coverage because building covering array ensures at least t-way coverage ensures at least we cover all the combinations specified by T. And it also helps to improve the scalability because we are saving some test cases. And this is some kind of theory and definitions, and let's see an example to see how it works. So suppose we have this, we want to build this covering array here. So we have specified that we have 4 parameters. So the k equals to 4, and t is 2, which means that the interaction level is 2. We want to do pairwise combinations. And assume that v is 2, which means that each value here, or each parameter here, can take only 2 values, say 0 or 1. And this is very common because many of the input parameters in real life, they are just like true or false, like different options. So, and let's try to determine the number of n here, which means how many test cases do we need to do a pairwise combinatorial testing. So how many pairs do we have here? If we have 4 parameters, how many pairs? Yeah, and that is 6. That is 6. And we can exhaustively write them down, which is P1, P2, P1, P3, P1, P4, P2, P3, P2, P4, and P3, P4. So we have 6 pairs here. And what we want is, we want to cover all the possible value combinations for each pair. So for each pair, we have, for P1 and P2, we have 0, 0, 0, 1, 1, 0, and 1, 1, right? So how many test cases do we need if we try to generate the test cases exhaustively? Actually, it's not simply. Sorry, I just made a mistake just now. Actually, we don't need that many. We don't need to simply times these two things up. Like there are 4 combinations per pair, and we have 6 pairs, so it's 24. That's straightforward. But as you can see here, P1, P2, P3, P4, they are like, if you consider it as 4 bits, because each one of them can only take 0 or 1, right? So in total, we only need 16 combinations to cover all the possible cases. P1, P2, P3, P4. We only have 16 choices here, actually. If we do 24, we will have some, we will end up in some duplicates. Is still, it's actually still the same. You can write it down and check, because we only have, let's assume each one of the parameters is like a bit here. We only have 4 bits, so we only have 16. Uh-huh. 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 No. Sorry, P1, P2, 0, 0, P3, P4, 0, 0. It depends, because this covers the pairs for P1, P2, 0, 0, P1, P3, 0, 0, P1, P4, 0, 0, P2, P3, 0, 0, P2, P4, 0, 0, P3, P4, 0, 0. So if we have this one here. And so we don't need 4 times 24, so 4 times 6, because with just 1 test case, we can already cover many pairs. So that's why it's 16 if we exhaustively try out every combination. And we can even shrink this number down, so we can even have less number of test cases to cover to make sure that each pair here can cover all its possibilities. So let's see why Let's see why we can do this with covering array. Oh, there's a flaw in this animation. This slide has a lot of animations, and I will see what's happening later, but let's try to continue first. So these are the pairs we can have, and we want to cover all the possible values for each pair of inputs. And if we do it exhaustively, we need 2 to the power of 4 test cases. And assume each value has 3 values. Each parameter has 3 values. How many test cases do we have? Do we need 3 to the power of 4 actually? If we do exhaustive, if we generate the test cases exhaustively. So with a covering array, we can just use 6 test cases to cover all the possible combination of to cover all the possibilities for each combination of a pair of inputs. And let's see why. And this is the covering. This is a covering array here. And let's go through the pairs one by one, the pairs of combinations. So the first pair is P1 and P2 here. So for P1 and P2, we try to cover 0, 0, 0, 0, 1, 1, 0, and 1, 1. So we can cover 0, 0 here with test case 1 for P1 and P2. And 0, 1 with test case 2. And 1, 0 with test case 3. And 1, 1 with test case 4. And we can also, let's move on to the next pair of test inputs. For P1 and P3 here, we can cover the case 0, 0 with test case 1. We can cover 0, 1 as well. We can cover 1, 0 with test case 4. T is 2, yeah. Why is the test cases they have every? Yeah, they have. You have to have every parameter to run the program, right? Normally. No. Yeah. So you still need to put in all the parameters in the test case. But you don't. But one test case can cover many pairs. The can cover the values taken by many pairs. So this is why we can save. This is why we can use some kind of design strategies to save the number of test cases. So the last pair of values we need to cover for P1 and P3 are 1, 1, which could be covered by test case 3 here. And let's move on for P1 and P4. So P1 and P4, we need to cover 0, 0. And we can cover it with test case 1. And we can cover 0, 1 with test case 2. 1, 0 with test case 3. 1, 1 with test case 4. And we can also check for P2 and P3. P2 and P3, we can cover the possibility of 0 and 0 with test case 1, 0, 1 with test case 3. What about 0, 1 for P2 and P3, which test case could be used? 6. Sorry, the 1, 0, which could be, yeah, which 0, 1 could be 6, could be 3, and 1, 0 could be 4. And what about 1, 1? 2, yeah. So far we only used 4 test cases to cover all the pairs. And let's move on for P2 and P4. So this is why you see a red dot in the slides. I missed one of the animations. So for 0 and 0, we can use test case 1 to cover the 0 and 0 for P2 and P4. What about 0, 1? 6? Yeah, 6. So now finally we are using 5 or 6. So what about 1, 0 for P2 and P4? 5, yes. And 1, 1 we can use 2 or 4. So let's move on for P3 and P4. So for 0, 0, which one can we use? We can use the first one. For 0, 1, we can use test case 4. For 1, 0, we can use test case 3. For 1, 1, we can use test case 2. So that's why we can use only 6 test cases to cover all the possible combinations and all the values for each combination. And you may wonder how is this covering array calculated? And calculating covering array is actually not very easy, as you could imagine. And there are several algorithms for calculating it. And there are stimulated annealing and genetic algorithms. And there are, we can also use greedy algorithms. And let's learn greedy algorithms here today because it's relatively easier. And we will learn genetic algorithms. But genetic algorithm is quite a general algorithm. It could be applied to different scenarios, and we will learn it next week in a different scenario. But let's learn the greedy algorithm here. How can we do this? So with the greedy algorithm, we are doing it step by step. So it's like we are building the covering array test case by test case. And the concept is very simple here. So each time when we try to come up with a new test case in the covering array, we will try to use the test case that can bring us, that can cover the most entries in the combinations. So that can help us to cover that can cover most number of combinations, and then we use that test case in the covering array. This is the key concept here. So let's come back to the previous example where we have 4 parameters, and this time let's try to make the parameter name simpler, A, B, C, and D. And we are trying to do two-way combinations, and each parameter here can take 2 values. Let's say 0 or 1 again. So the step 1, we can just use a random one to start with. So this is the covering array we have. So A, B, C, and D all taking the value of 0. And this is the table to maintain, to check whichever combinations we have covered. So for all the pairs here, we still have 6 pairs. And for all the pairs, we are covering the 0 and 0 case for them. So this is step 1. And step 2, can we come up with a test case that can introduce 6 new pairs? And the short answer is yes. The short answer is yes. And let's try to combine. Let's try to fulfill the coverage requirement for A first. So for A, it needs AB, AC, and AD. So AB, it already covered 0, 0. So let's try to cover 0, 1 for AB, 0, 1 for AC, and 0, 1 for AD next. And this time, we can cover these many combinations. So for AB, we are actually covering the pattern of 0, 1. For AC, it's also 0, 1. AD is also 0, 1. But for BC, we are covering the pattern of 1, 1, and BD also 1, 1, CD and is also 1, 1. So we can try to come up with this test case. And in each step here, what you can do is you can also try to exhaustively try out all the possibilities of test cases. And if a test case can bring the most number of coverage of combinations, we will append that test case into this covering array. And let's continue. So can we, after what we already have, can we come up with a test case that can introduce 6 new pairs again? And this time it's actually no. Let's see why. Because we already covered 0, 0, 0, 1 for 0, 0 and 0, 1 for AB, the pair of AB. And if we don't want to introduce some kind of duplicate, we have to use 1, 1 or 1, 0 here, right, for AB. So let's assume we use 1, 1. We fix 1, 1 for A and B. And then for C and D, we have to choose from 0, 1 or 1, 0, because 0, 0, if we don't want to waste effort. So because 0 and 0, 0 and 1, 1 have already been seen before, so we have to use 1, 0 or 0, 1. Let's assume we use 1, 0 here. If we use 1, 0, you can see that we can bring in a new coverage for AB, which is 1, 0. We can also bring in a new pattern for AC, 1, 1. For AD is 1, 0 is also new. For BC, 0, 1 is also new. But for BD, we have to suffer from a duplicate here, which is 0, 0. And for CD, it's a new one, it's 1, 0. And if we try to use the other choice here, 0, 1, then we will suffer from a duplicate of 0, 0 for BC. So we can't avoid suffering from some kind of duplicates here because we are almost reaching, we are filling half of the table here. So we have to bear with that duplicate. And this is how we come up with the third test case here. And let's move on. So we can continue. Just now we mentioned that if we try to avoid duplicate, we can consider one pair first. So for AB, let's continue the combinations for AB here. Since we already covered 1, 1, 0, 0, 0, 1, 1, 0, so we have to use 1, 1 for A and B. And for the rest of the parameters, since we already seen 0, 0, 1, 0, 1, 1 for C and D, let's just use 0, 1 to maximize the gain from this test case. And in this test case, we can have 5 more patterns covered. And now we only need to cover the rest of the table for B and D. And then we just need 2 more steps to deal with B and D. So we just need 2 more test cases for BD. And in this case, since we only test case 5 and 4, they are designed to cover the value pairs for the values for B and D. So we don't need to care about the values of A and C in these 2 test cases, because the combinations for A and C has already been covered by the first 4 test cases here. So that's why we need 6 steps here to build this covering array to save testing efforts. However, as you can see, greedy algorithm is actually very fast and practical. So it's very simple to implement. And it can provide near optimal test suites quickly, but it's only near optimal, like many scenarios where you can use greedy algorithm. So the limitation is that it may not be, it is not the optimal solution here. If we want the smallest test suite, it may generate some redundancies in certain cases. And so these 2 are actually talking about the same thing. So the other algorithms, like genetic algorithm, may give us a smaller set of test suites. But they are more complex and they will require more computational power to do. So let's just use greedy algorithm here. And that's about the limitation of greedy algorithm. And there are some limitations for combinatorial testing as well. So for combinatorial testing, it suffers from the problem of parameter explosion. So if we have too many parameters and each parameter could have too many values, then even if we limit the number of t to 2, we could still have too many test cases to deal with. And there are some constraints sometimes among these input parameters. So it may, if we just do the combination design here, we may end up in some infeasible combinations of test cases in reality, because some of the parameter combinations are not valid due to the constraints among these input parameters. And if the system is very complex, the combinatorial testing may not be enough to cover many corner cases. And in that case, we may consider to use some model-based testing techniques instead. So that's all about combinatorial testing. And let's have a 10 minutes break. I will see you at 2:52. So it's recorded, I think.
Oh. I'm just asking if a test case has every parameter. Why are we looking at combinations of 2 or 3? Like, what's the outcome of looking at that test?
The thing is, we are. The order is different. You should think the problem in a different order. So we come up with a combination first, and then we design the test case, not because we see the test case and then see what it can cover, what kind of combinations it can cover. So the idea is the rationale of combinatorial testing is to cover that interactions between parameters could cause problem. Just like in our last lecture, when we try to do mutation testing, we try to modify the condition from A is larger than B to A is larger than B plus 1. So so the relation between A and B is like interaction between parameters, right? So the rationale is that interactions between parameters could lead to errors, and we want to cover all the possible interactions between parameters. And we can try to cover all the possible combinations of all the values together, but that is not very doable in real case. That is that is how many? That is very, very large number, and we can't do that. But if we try to do a pairwise combinatorial testing, we will try to first find out all the pairs, and then find out all the possible values that each pair can take, and we try to build test cases which can cover the possible values for all the pairs. And if a test case can cover more possible values for more pairs, then it is more ideal test case, right? So we come up with combinations first, and then we think about the test cases. So this is the logic here. Okay. Okay, let's continue. So let's now move on to the second topic today, when to stop testing. So we have learned many testings so far. So we learned functional testing or black box testing. In this topic, we learned boundary value testing, we learned equivalence class testing, we learned decision table based testing. And we also learned non-functional testing techniques or white box testing techniques. We have learned about because white box testing is all about different coverage metrics. So we learned statement coverage, we learned branch coverage, we learned path coverage. We also tried to learn a little bit of data flow related coverage, the diffuse coverage. And we also learned fuzz testing or fuzzing, which is, you can have black box fuzzing, of course, and we emphasized on gray box fuzzing because it combines the advantage of black box and white box, and it is arguably the most effective or practical bug detection technique nowadays. And we learned different levels of testing. We learned unit testing, we learned integration testing, and we also learned system testing. And we also learned some Oracle-related testing techniques like differential testing, like regression testing, or metamorphic testing. And in this Tuesday, we also learned mutation testing, which is a special technique to evaluate test cases, the quality of other testing techniques. And just now we learned combinatorial testing. So we have learned all these testing techniques so far, all these concepts. So, but there's a question of when to stop testing. And this sounds like yet another type of testing called when to stop. But maybe you want to stop testing after this term because you have learned all these things about testing. So, but in reality, for software development, in the real software development scenarios, we need to come up with some stopping criteria for testing. And how do we, this is about how do we know that we are done with testing, right? So we need to come up with some metrics or criteria. And these are the things we can use as criteria here. So first we can use requirements. So what we can do is we can write test cases. We can write functional test cases according to the requirements, and then stop testing when all the requirements, when all the tests we have written are passed. But this is not ideal because we have learned it in previous lectures that we need to think about the actual implementation of the code if we have access to the code, of course. So what we can also do is we can try to use structural coverage to design test cases and to design some metrics, perhaps covering, let's say we can stop testing once we have covered 90% of statements, or maybe we can use branch or path coverage as well. We can say that we should stop testing if the coverage reaches maybe 90% or 80%. So this could also be used as criteria, but the thing is, the coverage, code coverage, is not a good metric for determining that the system is free from bugs. So we, in the example of assignment 1, the test suite, the last question of assignment 1, the test cases can cover all the paths, and that is the strongest structural coverage metric. And even the test suite can cover all the branches. The program could still have bugs. So using coverage or code coverage is not the ideal criterion here. And of course, in reality, most of the the most used stopping criteria is the budget. So, but if we run out of time, or if we don't have enough money to support testing, then we just stop. But this is also not ideal. The last, there's a mistake. The last thing is if we can also try to come up with a testing plan. And if we finish according to the plan, then we can stop testing. But this is also still not ideal, because we do plan is something we do before we do development, before we do testing. So we can't make sure that the plan can reflect the actual case. And sometimes we cannot always follow the plan. So that's why a testing plan is also not the most ideal stopping criteria. So the ideal case is actually to show some proof of dependability of the software. And software dependability. So we actually encountered this in lecture 1. I hope you can still remember that. That's a long time ago. And we learned the concept of software dependability. And there are 4 properties for software dependability. The first one is correctness. The second one is reliability. The third one is safety. The last one is robustness. So correctness means if a program is correct, it means that it is consistent with the requirements. And for correctness, we can't have, it's either yes or no. So we can't have a program is 30% correct, a program is 50% correct. That is not going to happen. So it's either 0 or 100%. So we have the second concept, reliability. So reliability is actually to measure the correctness of the program during some period of time. So during this period of time, this program doesn't run into a problem. Then we can say that this program is reliable. And correctness and reliability all talks about the occurrences of bugs or issues, but it doesn't care about the severity of issues. So if we count in the severity of the issue, we will think about safety. So safety is the ability of the software to avoid some very severe issues. And the last thing is robustness. So if the software can gracefully handle errors, then this software is considered robust. So we have all these dependability characteristics or metrics to use here. And we have to, but in lecture 1 we only learned about the concepts. We didn't learn how do we measure dependability. And let's think about how can we measure it step by step. So we know that finding faults, all the faults in a software is nearly impossible and always very expensive. And that's why many big companies, they are paying very high bug bounties to the white hat hackers who are reporting bugs to those for their products. So this is very expensive to find bugs, to find all the bugs, and it's impossible in reality. So we can always test more. So we must have some measurable criteria to define dependability. And let's think about the different properties here. So correctness is actually normally not used because you remember when we learned verification versus validation. So we can use verification to verify the correctness. We can use some very complex reasoning process like the formal verification. So we can do that for some small software, some small but critical software. But in most of the cases, we can't guarantee software is correct. And robustness or safety are also quite important, but they are not enough, and they couldn't be easily measured. And because it actually depends, these two properties are very dependent on the scenario. So if the environment is very tolerant, then this software, even if the software runs into some problem, it is not a safety issue. So, but if the environment is not very tolerant, is very sensitive, then this could end up into some disasters. So these two properties are also not a very good measurement here. So what we end up here is reliability. So we can try to somehow measure reliability to argue that the software is dependable. Because reliability refers to the observation that a software doesn't run into problems during a period of time. It's quite concrete. So we can measure reliability. And we can see that the definition is reliability is the probability of failure-free operation for a specified period of time in a specified environment for some given or specified purposes. So according to this definition here, we can also see that the definition of reliability depends both on the program or the target system and the user of the system, because it also depends on how the user uses this system. And because a buggy program could be a very good program for certain users if they don't use certain features. So they don't use those corner features. So informally, reliability is a measure of how well the user thinks the system could provide the services that they want. So reliability is actually is improved when the faults that occur in the most frequently used parts, because it relies on it depends on how the user uses the system. So if we can remove bugs in the most frequently used features, then we can have a big improvement in reliability. But if we try to remove some bugs in some corner or rarely used features, then the improvement of reliability is not very significant. So reliability depends on users, so we should remember this. And just now we talked about reliability could be defined and measured, and let's see how can we measure reliability. So what kind of metrics can we use here? The first metric is probability of failure on demand. So this is to calculate the likelihood that a service request will end up in a system failure. So the calculation is it's very simple. It's just failures divided by requests. So for example, if the POFOD equals to 0.001, it means that 1 out of 1,000 requests would end up in a failure for this system. And it should be used in the scenarios where a failure on request is serious. And we can also see that this is independent of the frequency of the requests. So although that 1 out of 1,000 requests sounds very scary, but if, let's say, that feature is only used once per year, then this is not a big issue, right? So it's only the probability of, with regard of the requests, number of requests, but it doesn't care about the frequency of the requests. So this is this metric. And the second metric is availability. So the availability of a system reflects its ability to deliver services when available. So it is calculated by using this formula here. It's also very simple. We can just use the uptime of the service divided by the total time since we run the service. So, and we should take repair and restart time into account, which means that if the system is during repair or is under repair, or it is restarting, then the system is not considered as up, so it's not counted in as uptime. And if the system runs into some logic errors or gives us some wrong answers or wrong responses, then it is not considered as a downtime. So let's say we have forcefully implemented some feature, but that feature won't cause the whole service to crash, to stop running. Then it is still considered as up. So availability here is a quick to give you a quick impression of availability here. So if we have this availability of 0.9999, it means that this system is 99.99% is available 99.99% of time. And if the system has an availability of 0.9, it means that we will have about 2 hours of downtime per day. And if this availability goes up to 0.9999, then the system is considered to have a downtime of 8.4 seconds per day. So this is just to give you some impression of the numbers here. So we can see that 0.9 is actually considered a very high value, right? But imagine Google is down for 2 hours per day, what will happen? So availability should always be very high for those publicly available or widely used services. So that is the second metric. And the third metric is rate of occurrence of fault, RCOF. So this is the frequency of the occurrences of bugs or unexpected behaviors. So it is related to time or frequency. So RCOF of 0.02 means there are 2 failures per 100 time units. So these time units could be seconds, could be hours, could be minutes, could be days. And this is most appropriate when requests are made on a regular basis. For example, if we are running a backend service, then it's better to measure this rate of occurrence of fault. And there's one last metric that we could use here, which is mean time between failures. So this is to measure the average time between observed failures. So this requires us to keep track of the timestamp whenever the system runs into a failure. And we also need to keep track of the time when the system has already restarted or resumed or continued execution. So we need to keep track of all these information. And an example is if MTBF is 500, then it means that the average time between two failures is 500 time units. So this is the definition here. And to assess reliability, because we mentioned that these reliability metrics could be measured, could be defined, we have to collect information during execution. So for POFOD, we need to measure the number of failures per a given number of requests. So we need to measure these two values. And for ROCOF, for the rate of occurrence of faults, we have to measure the number of faults as well, but we need to measure time in this case. And then if for MTBF, we need to capture the timestamp of each failure and the timestamp when the system restarts. And for availability, of course, we need to do similar things to MTBF, but we just need to sum up all the time intervals when the system is up. So these are the four metrics used for calculating or measuring systems reliability. And now let's come to an example. Remember the shortcuts here. These are the abbreviations for all the metrics and plus availability. And let's consider this example here. So assume that we have made 10,000 requests and we got a wrong answer for 35 requests and the system crashes on 5 requests. So what is the probability of failure on demand? Forty divided by 10K. So this is the number of failures we will have, and assume that we run the software for 144 hours. And during this period, we have 6 million requests, and the software failed on 6 of them. So what is the rate of occurrence of fault? Yes, 6 divided by 144, and that is roughly 0.04. What is the probability of failure on demand? Yes, 6 over 6 million. And sorry, what is the mean time between failures? Yeah, 144 divided by 6. Yes, that's roughly per day. So let's continue. And let's say a piece of software has a rate of occurrence of fault of 0.001 failures per hour. And it takes 3 hours to get the system up again after a failure. So what is the availability per year? So this is not calculatable by just thinking, but we can quickly do it during this on the slides. So what we need to do is we need to calculate the number of failures per year first. So we can use our COF times, because it has 0.01 hours failures per hour, and in 1 year we have 8,000 hours. So we will expect to have 8.76 failures per year. And then the availability is we need to calculate the downtime. So the downtime is because we need 3 hours per failure. So we just use 8.76 times 3, and we can get 26.27 hours of downtime. And then we can calculate and get the availability of 0.997 for this question here. So this is actually quite straightforward. So now let's come to one new type of testing here, which is called statistical testing. So rather than using tests to trigger faults, we can use tests to measure reliability, because just now all the metrics or measurements of reliability is unlike something happens after release. So when the user uses the software, some errors or faults may occur, right? So what if we don't have, we are not releasing the software yet? What if we want to measure the reliability without users? So we need to do statistical testing. And what we can do is we can try to generate test cases that is similar to how the users would use the system, and then we can try to record errors and other measurements to calculate all the metrics, and then we can specify a level of reliability according to the metrics, and then we can stop testing once the level of reliability is reached. So a key concept here for statistical testing is that we need to build up operational profiles, because we want to get the reliability of the system without users, and reliability depends on the behavior of the users. So we need to get the profiles of how the system would be used by the users, and this is the operational profile. So it actually reflects how the software is used, and it consists of classes of inputs and the probability of their occurrences. So this is to simulate some frequently used features of the software or some rarely used features of the software. So if a feature is frequently used, then we can have a higher probability for the inputs related to that feature. So this is why we need to have this. And it could also be specified in advance if other systems exist that performs similar actions. So we can borrow the operational profile from other systems similar to our target system. And of course, for new systems, it's often harder to specify. What we can do is we can consider beta testing to release the software to the users and collect usage data. So this can help us to build operational profiles. So we can observe how humans would use or how users would use the software to build up this profile. And of course, that is not all. So old systems could become new systems if we replace a lot of features of the old system. So the usage could change over time. So we should remember to update the operational profiles from time to time. And here are the key steps to do statistical testing. So the first one is that we need to study existing systems or the current system we are testing to form an operational profile. And of course, we can also use some other techniques to collect usage information to build this profile. And then we need to construct test inputs to reflect this profile. So remember, for each class of test inputs, we should associate it with some kind of probability of usage. So this is the second step. And the third step is that we should apply the test cases and collect all the metrics we just mentioned, like the number of failures during a period of time, like the number of failures for a certain amount of requests, or the uptime, the downtime, and so on. So after we have collected all these information, we can do the calculation of these metrics, and then we can use these metrics to evaluate the reliability of the system under test. So the key thing here is, you just need to take note, is that statistical testing can help to estimate the reliability without actual users. However, like many other testing techniques, statistical testing also has limitations. So first, it suffers from the uncertainty of operational profiles. So just now we mentioned that we should keep updating the operational profile, because in some cases, a rarely used feature could become a frequently used feature if the environment or the user group changes. So the operational profile may change over time. And the profile based on, because we can get operational profiles from existing systems, and we should be careful when we do this, because there are some discrepancies between the system we are trying to learn from and the actual system we would like to test. So this could affect the performance of statistical testing. And the second thing is, if we want to do statistical testing, we may suffer from a high cost of test input generation, because we need a large volume of inputs to trigger a failure. For example, to check for reliability, for example, we may end up in millions of test cases to trigger one failure in a relatively reliable system. And if we want the data to be statistically significant, we do need a large amount of enough values here. And the last one is statistical uncertainty, which is a limitation by nature for this statistical testing. So we need to generate enough failures to estimate reliability. So if we don't have enough failures of the system, we can't really argue that the data is reasonable. So, but this would also, on the other hand, tell us that the system is quite reliable. So, but it is hard to decide whether it's because the system is reliable, or because we have some bad design of operation profiles, or we have some bad design of test cases. So it's hard to tell. And in reality, what we can do is we can try to use whatever information we have already collected during the development to build up a model for the failure rate, for reliability. And normally this model would look like this. So the failure rate would drop the failure rate will drop during the development very fast at first, and then with more and more failures eliminated in the key features, the improvement of reliability becomes slower, or the dropping rate of failure becomes slower, and then we can set a particular level of failure rate, or according to those metrics, to stop testing and release the software. So this is normally how we do statistical testing. And that's all for the main contents today. And let's have a quick recap of what we have learned. So in today's outline, we don't have too many things, but we learned something new. And first, we learned combinatorial testing. Combinatorial testing is also known as T-way testing, or T-wise testing, or N-wise testing. T-way testing or N-wise testing. So the key idea behind combinatorial testing is that interactions of input parameters or configuration options of the systems of a particular piece of code or a program or a system could end up in or lead to errors. And this is the rationale of combinatorial testing. And what we want to achieve is to collect all possible n-wise combinations of, like pairwise combinations, or four-way combination, or two-way, three-way combinations. We collect all the combinations and try out all the values for each combination with our test suite, and we try to build this test suite, and to build a minimal test suite that can cover all the combinations and all the values for each combination. We should consider building the covering array. And to build covering array, we can use different algorithms. And what we learned today is to use a greedy algorithm to build the covering array. So we will try to build the covering array test case by test case, and each time we try to append a new test case into the covering array, we try to select the one that can cover the most number of combination patterns. So this is how we use greedy algorithm to build this covering array. But remember, this greedy algorithm is fast, is easy, but it may not give us the most optimal covering array. So that's the drawback of using greedy algorithm to build covering arrays. And we also learned some limitations of combinatorial testing. So it has the problem of parameter explosion, similar to what we have learned for path explosion. And it's all because of combinations of paths or combinations of parameters. So we could have end up in an infeasible amount of test cases to build. And for combinatorial testing, it may also suffer from several other limitations, but parameter explosion is a key one here, limiting its real-world application. And we also learned an important thing about when to stop testing in real-world development. So we learned that we should use some kind of metrics to be used as the stopping criteria. And the best criterion to use is to argue that the system is already dependable. And for dependability, we have a callback to the first lecture, the dependability, and there are 4 different properties: correctness, reliability, safety, and robustness. And we think through each one of the property here and found that the reliability is the most suitable one to be measured here. And because it has some concrete definition of whether it's not very as strict as correctness. It just requires the system to run into no errors during a period of time, during a specified period of time, in a specified environment with a specified or a given purpose. So it is more practical to measure than correctness, and it is more measurable than safety or robustness, because those two, the definition of robustness and safety, are more related to, they are more affected by the environment. So we need to calculate, so we can calculate, we use reliability to represent software dependability here. And we have some metrics for measuring software reliability. Actually, we have 4 metrics. So the first one is the probability of failure based on requests, and this is calculated by dividing the number of failures by the total number of requests. And the second one is related to time instead of requests, so which is the rate of occurrences of failure. And this is divided by this is calculated by dividing the number of failures with the number of time units. And we also have the third metric of calculating the availability, and it is calculated as the time units, the number of time units of uptime divided by the total time of executing the target. And we have one last criteria, which is to calculate the, I forgot the last one. I forgot the last one. Oh, mean time between failure. Yeah, we need to calculate the average time between failure, and this is actually the more used ones in some big companies. So we need to calculate the average time between 2 failures, and in order to calculate this, we need to keep track of the timestamps whenever a failure occurs, and the timestamp when the system restarts. And with all these metrics, we can do statistical testing. And for statistical testing, the purpose is to simulate how the users would use the system in reality. And we need to design, we can use the test case designing strategies we have used before to design these test cases. And we can, but remember, we need to associate each class of tests with a probability of usage in reality. So this is to simulate how the users would use the system. And then we can run the tests and observe for all these, to observe and calculate all these metrics here, and use these metrics to measure or to estimate the reliability of the system. And if the system is considered the reliability reaches certain level, then we can stop testing and release the software. But that is when we can stop testing, but that is not the stop of this course. We still have 2 more topics to be covered next week, which is all about how can we automatically generate test cases and with some advanced algorithms. So that's all for today's lecture, and thank you for coming.